I wanted to talk to you for a minute about something called a colligative property. Now, a colligative property of a solution is a property that only depends on the amount of solute in the solution. It doesn't matter what kind of solute it is, it just depends on how much there is. So adding more solute will change the property one way, less solute will change it in another way. And there are two main ones that we're going to look at. We're going to look at freezing point depression and boiling point elevation. So the first one is this, is that anytime you add more solute to a solution, what happens is that the freezing point gets lower. For instance, pure water will freeze at 0 degrees Celsius, so the freezing point is 0 degrees Celsius. If you add a solute to that to make a solution, the freezing point becomes lower than 0 degrees Celsius. So the freezing point is depressed, it's pushed down by adding that solute. And the more solute you add, the lower the freezing point gets. So for instance, if we've got water, and I'm just going to draw this in view of the atoms, so think of these as the atoms, or rather molecules, that make up water. As this liquid water gets colder and colder and colder, these atoms are losing energy, and as they lose energy, they fall into a regular pattern, and that's what makes the solid. So what's happening here is basically that there are, you can think of them as being small forces that would stick these molecules together and arrange them in an orderly pattern. As they heat up, these start moving faster and faster until they have enough energy to break away from each other. So what happens is there's a certain amount of energy that you have to add in order to break those and get a liquid. Now, this is an orderly arrangement when you just have water. If there's a solute involved, now we have something else, and I will grab another color for this. Now we have something else in our water. So let's say I added sugar to it, for example. So when I add the sugar to the water, now in order for this to freeze, to have this orderly arrangement, the water would like to do this, but it's got all these sugar particles in the way. And what this means is that the water molecules are not connected together as strongly as they otherwise would be, which means they need less energy to break apart from each other, which means that all in all, this will turn into a liquid at a much lower temperature. So again, because these sugar particles are in there kind of keeping the water from joining together like it otherwise would, it takes less energy to cause those water molecules to break apart into a liquid, and thus that brings the freezing point down, or the melting point down. Both mean the same thing. So this has some nice practical effects. For instance, you might notice when it snows, one of the things the city will do is that they will salt the roads. And so what happens is when the snow lands, it would normally form into ice. But when you add the salt to this, that breaks apart into its constituents, sodium chlorine ions. And so now you've got all this sodium and chlorine messing up the formation of that nice ice crystal. And so what happens is that it has to be colder and colder and colder for ice to form. And since you don't want ice forming on the road, this is a nice thing. By throwing salt on there, you can keep it from freezing. So if the temperature gets to, say, -2 degrees Celsius, if you've got enough salt on the road, it still won't turn into ice. It'll just be liquid, which makes driving much more manageable. So that phenomenon is called freezing point depression. So again, the point at which it freezes gets lower. Now at the same time, we have this thing called boiling point elevation, which is another colligative property. And it turns out that when you add a solute to a solvent, it causes the boiling point, the temperature at which that boils, to increase. And here's why. If we have, and I'm going to get rid of this, but let's say we have our water, and we're going to turn that into a gas. We want to boil this. Well, what happens is that as this is sitting here, you get what's called vapor coming off of this. Some of these atoms are moving fast enough to turn into a gas over top of the liquid, which is called a vapor. And that vapor exerts something called pressure, which is force over an area. So that is, those atoms from the vapor bumping into the surface are bumping in with some amount of force. You can also measure this on the walls of that, but that's called vapor pressure. And this liquid will boil when the vapor pressure becomes equal to the air pressure around it, so the atmospheric pressure. The atmosphere is always pushing down on us. And so when the vapor pressure coming off of this matches the atmospheric pressure, this will boil, and it will all turn into a gas. Now, what happens is that as temperature increases, vapor pressure increases. So basically, as the temperature gets hotter, this thing will boil, which is what we're familiar with. When you have a solute added to this solvent, though, so let's suppose I put my sugar back in there, and now I have all these sugar atoms floating around. Those sugar atoms will actually, oh, forgive me, computer warning popped up. These sugar atoms will actually cause the vapor pressure to go down. So now there's less vapor pressure than there otherwise would have been. And that means that, remember, increasing temperature increases vapor pressure, so now we have to increase the temperature even more to get the vapor pressure back up to atmospheric pressure, and so this thing will boil at a higher temperature. This is why if you're cooking pasta and you throw some salt in the water will now boil at a higher temperature. And the more salt you add, the higher the temperature that it boils at, which will allow you to cook the pasta faster because now the water is hotter. So for instance, water normally boils at 100 degrees Celsius. Once you add solid in there, that begins to rise. So now it'll boil at, maybe if you add enough, 101 degrees Celsius, so on and so forth. So again, two colligative properties, properties that only depend on the amount of solute, are freezing point depression and boiling point elevation. As you add solute, the freezing temperature goes down and the boiling temperature goes up. And what that does is create a wider range where the solution can stay a liquid. And another interesting application of this, where we get both at the same time, is antifreeze in cars. So you add antifreeze, which is this liquid, into your car, and that mixes with the water that's used to cool the engine. This has dual purpose. Since it's called antifreeze, you might think that it prevents freezing, which is true, because it mixes with the water that you're using for cooling. And since we now created a mixture, the amount that you have added in there causes the freezing point of the water to go down. So now it has to get colder for the water in the car to freeze. Likewise, the boiling point is raised. So now if your engine's running really hot, you have to get that water hotter than 100 degrees Celsius in order to boil it. So antifreeze is like all-purpose wonder juice for the engine as far as making sure that it doesn't freeze and it doesn't boil over at the same time. Very nice image of chemistry in action.